Welcome back. We're at lecture 51, day 2 for us in substitution or change of variable method. We've got several examples yesterday, but we kind of started with some simple ones to get the kind of flavor of what it is we're actually trying to do. Trying to take an ugly looking integral problem. Yesterday they were indefinite integrals. Make a substitution because there's kind of an internal function, so we're going to let u or some other letter that we choose equal that ugly internal f of x, and then see if we can anti-differentiate it by making it look a little easier. Once we're done integrating, we need to switch it back. Now, it may not have looked like this yesterday, but here's, in essence, in terms of kind of math principles, what we were doing. The first one, the substitution rule. So we see some function inside of another function. We let u equal that function. Normally, it's not the square root or raising to the 7th or something else that's a problem. It's the thing that's in the parentheses that's the problem. So we let u equal that ugly quantity in parentheses. So we're going to see some f of this internal function. So we have an f of a g of x. But we also have to have the g prime present. And if the g prime is present, then really what this is we've changed the original problem from an x problem to a u problem. Okay, f of u, comma, or also with du in the integrand. So that's kind of the way we approached it yesterday. But this is more of a chain rule look at what it is we're actually doing. So if that rang a bell yesterday, or let u equal something, and do we have du? If not, is it correctable? That approach, that's fine, but that's more of a chain rule look. We started this right at the end of class, and we'll get some more of this today. What if it's a definite integral? What if we have an integration with respect to x, and we're going from a to b? Well, those are x values. That's actually x equals a to x equals b. So once we change it to a u problem, notice what they have for limits. We've now got to adapt our limits to go along with our original u substitution. So that internal function was the g of x. Now the internal function is u. So we've got to change our x values to u values. Or wait till you're almost done with the problem. You have everything back in terms of x. Reinstitute your original limits of integration. So that choice is up to you. But we cannot use the original x limits of integration if we've changed the problem away from an x variable. We didn't talk about this at all, but we will encounter a problem or two now and then like this. If the function is continuous on some symmetric interval, negative a to a or negative 7 to 7, and if the function is even, think of what that picture is going to look like if we have an even function. What kind of symmetry is that? With respect to the y-axis? So our picture might look, whatever this curve looks like over here, it also looks the same over here, right? So if we're going from negative a all the way to a, why can't we just take one of the regions, 0 to a, and do what with it? Double it. And that's exactly what this says. So if you're dealing with an even function on some symmetric interval, negative a to a, just take it from 0 to a, or negative a to 0, take half of the interval, and double the result. The fact that you've got 0 involved here means it's probably going to be a little bit easier to evaluate. That's the advantage. So having a mental picture of what's going on helps, and then you can shrink it down to that. If it's odd, what type of symmetry do odd functions have? To the origin. Okay? So whatever the function looks like here, its symmetric image down here is the same, right? So if we've got this region and this region, what's going to happen to the two regions? They'll cancel each other out. So the end result is 0. So you could have, in the book, I'll find that there's a hideous problem. I mean, it's a ridiculous integrand. And you're thinking, oh my goodness, how in the world am I going to integrate that? And then evaluate it. Well, you don't have to because it's an odd function and we have a symmetric interval. So you can just basically, if you notice that, you can just write down your answer. The answer is 0.
And how do you know if a function's even or odd?
Okay, right here, there's even. If you can put in x or negative x into the function and it doesn't make a difference, that's an even function. So
Okay.
squaring to the 4th, absolute value, those kinds of functions.
Oh.
It's even, and if you put in negative x and it's the negative of the f of x, then that's an odd function. So that'd be like cubed to the 1st to the 7th. Give me a trig function that is odd. Here's a picture. What trig function kind of has tangent? Sine is odd, isn't it? Sine function. So if you were to graph it, doesn't it have symmetry to the origin, right? So you could get the rest of the picture going here to validate that, but it does have, the real reason why is we're trying to determine if it's odd or not, is the sine of negative x, is that the negative of the sine of x? Well, let's say x is an acute angle. The sine of x would be positive, and then we would negate that. What about the sine of negative x? Well, that takes us down into the 4th quadrant. What is the sine of a 4th quadrant angle? It's negative, right? So this is the same thing as negative the sine of x, because x is the reference angle. Those are the same. So it is an odd function. What's an even function? Cosine is even. And you can do that from the graph. We've got our cosine graph that has this type of symmetry going on. This region and this region are the same. Is the cosine of negative x exactly the same as the cosine of x? X is a 1st quadrant angle. Cosine of x is positive. How about the cosine of the 4th quadrant angle that is exactly the same size? They're equal, right? 1st quadrant, 4th quadrant, cosine is positive in both cases. So it is an even function. That doesn't come up very often, actually, but now and then in a strange problem, that will come in handy. Okay. So I don't know how many of these problems are from your book. I intentionally went to another book that I've taught out of before to get some of these problems, but some of them might be the same as the ones in your book. This is not a real easy problem for a couple of reasons. It's our first definite integral problem, so these are x values. Whatever this indicates, that's what those limits are. So from x equals 1 to x equals e, that's kind of a strange limit of integration. The other difficulty with this problem is that the way it's written kind of looks like a fraction. I think it helps to, in a lot of problems like this, to rewrite it as natural log of x times 1 over x dx. That helps me visualize what type of substitution might actually work. Does that give a hint to what we might want to let u represent? Natural log of x. Now, why did you think that? Because the derivative is 1 over x, and it also happens to be in the integrand. So in its original form, it may not be as clear that there's a 1 over x there. Sometimes it helps just to look at it separated, natural log of x separated from the division by x. So the derivative of the choice that we've made for u is 1 over x dx. Let's see what our integral problem looks like now in terms of u. That's a u, right? And everything else, it looks like we don't need to make any corrections and compensations. 1 over x dx is actually du. Tremendously easier looking than the original problem. Not to say that you can't look at that mentally, convert it to this, kind of do this substitution in your head, but regardless, you're going to come up with this type of integrand. It's clearly, to me, easier than that one. Now, let's go ahead and change the limits of integration for this problem. We need u values here and here. Right now, we have x values. But we do know the interrelationship between u and x. So, if u is equal to the natural log of x, and x is 1, what is u equal to? What's the natural log of 1?
0.
That's 0. So where we had an x value of 1, we're now going to have a u value of 0. Now the other limit, we do know again the interrelationship of u and x. So u equals natural log of this specific x value, which is e. What's the natural log of e? 1. So our limits changed from 1 to e in terms of x to 0 to 1 in terms of u. Now you can finish the problem in terms of u. That's the advantage of changing the limits. You don't have to change everything back to x and then reevaluate. I think it's about the same amount of work, personally, but that is a slight advantage at this point. We can finish the problem. What's the integral of u with respect to u? U squared over 2. We don't need a plus c because it's a definite integral. We have new limits from 0 to 1. So that is 1 squared over 2 minus 0 squared over 2. 1/2. So the area under this curve, kind of a strange curve, natural log of x over x, from 1 to e, kind of strange limits for the curve as well, is a nice clean value of 1/2. Now, if you want to change the limits and finish the problem in terms of u, by all means do that. If you don't want to do that, we could, at this point in time in the problem, when we have u du, you could just put a little mark there to acknowledge the fact that it is a definite integral. And I'm going to wait until I get it back in terms of x to reinstitute the original limits. Integrate, that's u squared over 2. And now that we've integrated it and we have u squared over 2, let's substitute back. For every u, we want to replace it with a natural log of x. Now that it's back in terms of x, you can reinstitute these and basically plug in the numbers. Natural log of e squared over 2 minus natural log of 1 squared over 2. Do you see anything that is numerically different from what we had in the previous version? No. We just do the evaluation now of the internal function. So the natural log of e is 1, so that's 1 squared over 2. The natural log of 1, which we did in the other method before we did the integration, is 0 squared over 2. So the result's the same. It just kind of matters where you do the evaluation of the original limits. Do you change them, or do you wait till you're ready to evaluate your final result? Then they become those numbers. Questions on that problem either way? I don't have a preference. If you have a preference, then you go with that method and solve it from there. There's an example problem in your book that's similar to this one, slightly different, but the method will be the same. Kind of a function is x to the fourth plus 1.
Even.
That's an even function, right? That's really 1 times x to the 0, so 0 is an even number. So because that's even, whatever that looks like over here, it looks the same over here. So if we're going from -3 to 3, we might as well just change this problem and go from 0 to 3
And then double the final answer.
and double it. Does that work, since it's even? What's the integral of x to the fourth?
X is 5 plus
It-
x.
Plus x. That's what we're going to evaluate from 0 to 3. So no u substitution in this problem. It's just you recognizing that it is an even function. So 3 to the 5th over 5 plus 3. If we put in 0, what do we get? Here's the advantage. 0 to the 5th over 5 is 0, plus 0, so everything is 0, right? So that's how it actually saves time. So 3 to the 5th, 3 to the 4th is 81, times 3 is 243. Does that sound right? Over 5 plus 3. Get that in fifths, right? Which would be 15 fifths. Add it to 243, 258.
Yep.
And then double that, which would be 516. 516 over 5. So not substitution, just a recognition that it's an even function. Questions for that one? Moves. In fact, let's do this problem in its original form, and then let's also do this problem by flipping the numerator and denominator. And they look, I mean, obviously they're very similar integrands, but the methods by which you do the problem are very different. So what types of things would you think about as far as substitutions and derivative rules that would help you decide what to let u represent in this problem?
Could u is e to the x plus 1.
Okay, now if you thought that, which several of you did, what makes that have a chance of working in this problem?
The derivative of 1 is 0.
And the derivative of e to the x is itself. So those two thought processes in this problem, the choosing of the denominator as u, and then what's the derivative of something that has e to the x in it is e to the x dx. So where are we headed with this problem? By choosing the denominator to be u, natural log. So we're hoping we're going to come up with something in this format, 1 over u du. So the numerator, e to the x dx, is really du, right? So we've got a du in the numerator. And the denominator, e to the x plus 1, is really u. So is that this format? It is. And if you don't like du over u, you can write that as 1 over u du. It's the same thing. And what is the integral of 1 over u du? Natural log, absolute value of u. This is an indefinite integral, so plus c. And we can finish by saying it's the natural log of what? And no evaluation necessary because we don't have any limits of integration. Now, if we're sure that's positive, all the time you can drop the absolute value notation. Is e to the x always positive?
Yeah.
And if you add 1 to it, certainly positive. So if you want to just put parentheses, that's fine. Or if you want to make sure, then you can just leave the absolute value notation. All right, we're going to flip that problem. And the method will be very different. One of the reasons it's got to be very different is we've now got e to the x in the denominator. We'll never do a problem that has du in the denominator. If we have a du, we want the du to be in the numerator. So that original method that we tried isn't going to help us. Plus, we've got e to the x denominator, dx numerator. That becomes an issue. Any suggestions?
Separate them.
Separate it. Okay? Whenever you have a sum or difference in the numerator, you can write it as each term of that sum or difference divided by the single term in the denominator. So this problem is the same as e to the x over e to the x plus 1 over e to the x. It's kind of going backward algebraically, but by going backward algebraically, it makes this problem a doable problem. So e to the x over itself is 1. Gosh, I can integrate that. How about 1 over e to the x?
Natural.
No.
Oh.
What is it rewritten? I just want to rewrite it.
1 over e to the x.
1 over e to the x is the same thing as e to the negative x, right? So we can integrate this piece separately from this piece, and we'll be done with the problem. Actually, there is no u substitution in this problem. I guess you possibly could set it up here for e to the negative x, but I think we can think through the signs and come up with the right answer. What is the integral of 1 with respect to x? X. What's the integral of e to the negative x with respect to x?
Negative e.
Negative e to the negative x. Does that work? If you took the derivative of that, would you be back here?
Yes.
Plus c. Now, when I said you could use a substitution here, and I can tell that some of you are kind of already going through this process in your head by the fact that several of you came up with that answer. There's really what we're doing. We're integrating e to the negative x with respect to x. You could, let's let u equal negative x. What's the derivative of u? Negative 1 dx. Here's our e to the u. Do we have du? No. We need a negative 1 inside and outside. There's our du. So there's e to the u. There's du. What's the integral of e to the u du? E to the u with a negative 1 out in front. So we've got all that right here. So it's kind of a lower level substitution that I think several of you are beginning to do that in your head already. How many of you could do that in your head? I like that look. I get that look in my own home from time to time, like, what kind of an idiot are you? So I'm used to it. Okay, what's our choice then for you?
4 minus 3 squared minus 2x.
The ugly thing that's being raised to the fourth? What leads you to believe that that has a chance of working?
You'll have the same variable.
You'll have the same letters when you take the derivative of that inside function. Is that correct? You're going to have an x from this, and you're going to have an x squared from this, and they're both there in the numerator. It has a chance. So we'll know here in about 15 seconds if it's going to work. What's the derivative of u?
Negative 6x minus 6x squared.
Is it going to work?
Yeah.
You can just multiply.
Right.
By
It's going to work
1/6.
because we're dealing with an x plus an x squared, and we can convert this by what? Factoring out a negative 6? And I'm sorry I didn't put my dx there. Should have. Negative 6 times x plus x squared dx. So we've got that. We've got x plus x squared dx, and we can correct for what we'd like. So how do we do that? We haven't done that on a problem yet today.
Negative 1/6,
Okay?
Bring it up,
and then
like,
And
1
negative.
over u to the 4th.
So we need the negative 6. We can multiply by negative 6. You can't just change the problem. So we have to correct the multiplication by negative 1/6, which is dividing multiplication by negative 6, which is multiplication by negative 1/6. So we're stuck with that. Don't forget that. So the numerator is what?
du.
Now that we've got the negative 6, let's gather that in. That is du.
Yeah.
And the denominator is
U
U to the 4th.
u to the 4th. Much easier looking. If you don't like the way that looks still, you can say that's u to the negative 4th du. Those are the same, whichever way is preferred for you. Do that. What's the integral of u to the negative 4th du?
U to the negative
U to the negative 3rd
third. I don't
over negative 3. It's an indefinite integral, so we've got a plus c. We've got a negative 1/6. We're dividing by negative 3, so the net of that is what? Positive 1/18. And then we've got u to the negative 3rd. I don't think I left enough space, did I? Because u is kind of lengthy. So let me try it again. U to the negative 3rd. What is u? 4 minus 3x squared minus 2x cubed. Does that work? So you do have to, I guess, kind of pace yourself or something on these. You can't, and you'll get better at them. I can kind of tell that you're better at them today than where we were in the middle of the class yesterday. But you still kind of have to go slowly, or reasonably slowly, so you won't lose signs, SIGN signs, or corrections or correction factors. So you can speed up the pace, but just don't leave those things out. Okay, I don't think we did this one yesterday. Correct me if I'm wrong here. Does that look like something we did yesterday?
No.
Okay. You want to let u equal the square root of x plus 3? It's a little strange, isn't it? Why don't we rewrite it?
No, we can help it.
Isn't that really a 1 over the square root of x? So let's try that. Let u equal the quantity that's being raised to the second. Let's suppose this doesn't work. Do you have a backup plan? Square it out, divide everything by the square root of x. We're going to get a solution. And squaring something is not, like, outrageous. So we could do that in a matter of a few seconds, divide everything by the square root of x. We could get an answer. But I think this is going to work, because the square root of x is really x to the 1/2. That's one of the reasons why I chose this example. I think once you see these things and how they work, then when you look at a problem, you say, oh, we've done one similar to that. I think I can accommodate that square root of x that's in the denominator because that is part of or all of du. What's the derivative of x to the 1/2? 1/2 x to the negative 1/2. Derivative of 3 is 0. X to the negative 1/2 would be 1 over the square root of x. That looks kind of nice, doesn't it? Because we've got one of those. Okay, what do we need inside the integrand that we don't have that is able to be corrected for? 1/2. We multiply by 1/2, we have to multiply by 2. Everybody see why we needed the 1/2? Because du has a 1/2 and a 1 over the square root of x and a dx. So all of that circled stuff right there is du. And this is really u squared. Got a 2 out in front. Look better? U squared du, does that look better than that original ugly thing we started with? Integral of u squared du. U cubed over 3. So we've got 2/3 u cubed plus c will replace u with what it was originally before we did the substitution. So the substitution method actually did work. Questions on that? Anybody? Is that all right? So I've got one more example here. And I'm thinking about another problem that I didn't write down here that I probably should have. So I've got 2, but if you've got a WebAssign problem that you've started with and you want us to look at that today, we're going to have some time to look at that. What are some thoughts, Brendan?
Is that a 3 or is that a 2?
The exponent here
Mhm.
is a 3. Sine cubed of x, cosine of x dx. What are some thoughts that might...
equal the cosine?
Say that again,
Cosine?
Catherine.
Let u equal the cosine.
Let u equal cosine. Okay. If that's going to get us somewhere, we'll know when we find du. What's derivative of cosine? Which is kind of okay, but we don't have just sine. We have sine cubed. So it doesn't mean that, we're failures now. We tried something and it didn't work, I think I'm going to go run and hide. No, we're going to try something else. What else is going on here? Some nice interrelationship between sine and cosine that might be helpful. I want that to be du. I want cosine of x dx to be du.
Just sine of it.
Okay, let's let u equal sine of x du. Derivative of sine is cosine. It's going to work?
Yeah.
It's going to work. So this is du. That cleans that up quite a bit. And here's kind of the final decision maker. That, can we write that in terms of u?
Yeah.
That's u cubed. So this problem is a more complicated looking version of u cubed du. What's the integral of u cubed du? U to the 4th over 4. And then where we had a u, we can replace it with sine of x. End of problem, right? So if you have a sine or a cosine to a power, and then you have the other function out there kind of off by itself, a single sine or a single cosine like we had here, try to let that single sine or cosine, to let that be du, and see if you can't convert the other stuff that's present into the form where it is u. So that works here. One of the problems that I was going to choose had a 2x in it, double angle. I just saw another one while I was going through there that we probably should look at. Because we're really looking at all kinds of substitution. This has a type of substitution in it. Can you think of a function? We take the derivative of that. I like that. Save that thought. Who said that? Casey? Can you think of a function that we can take the derivative of that function and get tangent? Do we have something like that? We know how to take the derivative of the tangent. That's the secant squared. Do we have anything that we could take the derivative of that and get the tangent? I don't think we have anything like that. So Casey made a recommendation. Change the tangent to
Sine over cosine.
sine over cosine. I like that. I like where it's headed, but we've still got some work to do. Okay, let u equal cosine. So where are you headed with that choice?
Because you can't have du in the bottom.
Okay, there we go. We know that if we let u equal the sine, then we'd have du on the bottom. That's not going to help us. So let's make the other choice. If u is on the bottom, then we're hoping du is on the top, and where are we headed with that? Du over u, what is that? Natural log. So we're kind of headed hoping that this will be a integrand that will integrate into a natural log. Derivative of u is negative sine.
Yeah.
So our problem becomes, well, it's not exactly letter perfect. Do we need to make a correction? Negative 1 here and negative 1 out front. So now that we have the negative 1, the numerator is du. Denominator is u. So we're getting there. You can use that format if you want to, but if that is one that you don't quite recognize yet, just convert it to 1 over u du. Now this negative sign is going to have an interesting result of how we can get rid of that negative sign when we finish. You can keep it, or you can have a choice of getting rid of it too. Integral of 1 over u du.
Natural log of u.
So negative 1 natural log of
Cosine.
cosine of x. That is a possible answer. That is a correct answer. Probably, if you were to look this up, if this were a problem that you were looking up a solution, you're probably not going to find that answer. What would you find?
Natural log of cosine x minus c.
No.
Cos-
What could I do? This is a natural log. You can't do this all the time. But when you have a natural log, if you have the natural log of, let's say, 3 to the 5th, isn't that the same thing as 5 times the natural log of 3? Can't you take that 5 and bring it out in front, right? Well, if that works, can't you do that in reverse? If you have the 5 there, could you not replace it in that position? So we have a negative 1 out in front. Where could we put that negative 1? We could put it right there. So natural log of the cosine of x to the negative first. Well, what is the cosine of x to the negative first? What's 1 over cosine of x? Secant. So both of those answers are correct. But I have a feeling that if you were to check a solution, you'd probably find that one on this problem, as opposed to this one. So if you can only do that when it's a natural log, and that refers to this property of logarithms. All right, I did come across a double angle identity. And I'm not sure if it was this book. Don't know if we should. Yeah, let's finish with this one. It's not the double angle. I guess it was another book I was looking in. This one is substitution, but it's also kind of a trick. So you're not really expected to know the tricks. But in case you come across this exact function, let's at least plow through it one time in here so it doesn't look like this complete mystery answer. Do we know something that we could take the derivative of that something and get secant? We don't have anything like that. So here's the trick that happens to work on this problem, and you'll see why the trick works. Let's multiply the numerator by secant plus tangent. We can't do that without also multiplying the denominator. Is that the same problem? I'm not doing anything inside the integrand and bringing it out in front, because that would not be legal with variables. So the numerator, have any of you seen this before? You've seen it if you've had some calculus? The numerator is secant squared theta plus secant tangent. That's a big hint as to how this problem gets solved. Do you recognize those things in the numerator? Secant squared is the derivative of tangent. Secant tangent is the derivative of secant. So we're at a point now that we can decide what to let u represent. Good. The denominator. Is that going to work? Actually, this works very cleanly. Derivative of secant is secant tangent. Derivative of tangent is secant squared. So where are we headed with this? I think it's going to work.
Natural log.
But we're headed toward the integration being a natural log, because the numerator is du and the denominator is u. And I'm going to avoid that little intermediate step I've been writing down. Du over u is a natural log, right? And then we've got that ugly choice for u, but then we're done. Secant theta plus tangent theta plus c. So what is the integral of the secant of theta? That is. And fortunately, we don't have a lot of problems that require some little trick. But that one is one that does. Okay, any WebAssign question that is bugging the living daylights out of you, and you want to at least get it jump-started in class? Does that mean you're done with them and they're easy, or you haven't even looked at them?
Both.
One of those, some of those, okay? All of the above. Okay, well, we are done, and I will see you on Monday.